For most of recent history, the moon was treated like a chapter humanity had already finished writing. During the 1960s and early 1970s, the Apollo program landed 12 astronauts on the lunar surface. They gathered rocks, planted flags, and proved beyond any doubt that human beings could walk on another world. And then, almost abruptly, it stopped. For nearly half a century, the moon became a place humanity had visited and moved on from, a closed file in the history books. That has changed completely. One country keeps returning: orbiters, rovers, sample return missions, and now concrete plans to send astronauts. On the surface, it might look like the opening moves of a new space race, but the actual motivation runs far deeper than national competition. China is not simply exploring the moon, it is preparing to use it. Understanding why requires looking at how the whole effort was designed. Because none of this happened by accident or in a hurry. China's return to the moon was built around a carefully structured long-term plan known as the Chinese Lunar Exploration Program. Rather than rushing to put astronauts on the surface, planners laid out a deliberate, sequential roadmap where each phase would build directly on the success of the one before it. The sequence was clear. First, orbit the moon and study it from above. Second, land robotic explorers on the surface. Third, retrieve samples and return them to Earth. And finally, develop the technologies needed for a lasting human presence. No phase could begin until the previous one had succeeded completely. The first mission launched in 2007, Chang'e 1, named for the moon goddess of Chinese mythology. It became China's first lunar orbiter, spending more than a year mapping the surface and producing detailed three-dimensional images of the terrain. 3 years later, in 2010, Chang'e 2 dramatically improved on that work, capturing high-resolution images that allowed scientists to identify promising landing sites across the lunar surface. These early missions never captured public attention the way crewed landings do, but they accomplished something essential. They produced the most detailed geological maps of the moon that China had ever created, helping researchers pinpoint regions that might contain valuable resources. That groundwork would shape everything that followed. The first true breakthrough arrived in 2013, when China achieved its first successful lunar landing with Chang'e 3. For the first time in nearly 4 decades since the Apollo era ended, an active spacecraft was operating on the lunar surface again. Chang'e 3 carried a small robotic rover named U2, meaning Jade Rabbit. Almost immediately, it began transmitting data that caught scientists off guard. As U2 rolled across the surface, its instruments analyzed the composition of nearby rocks and soil. The results were unexpected. Some of the rocks in the region were basalt, volcanic rock formed from ancient lava flows. But these samples did not match the chemical composition of the rocks scientists had studied from the Apollo missions. They were genuinely different. The mineral arrangements and chemical signatures suggested that parts of the moon had formed through volcanic processes unlike anything previously documented. The implication was significant. The moon's geology was far more varied than researchers had assumed. For decades, almost all human understanding of lunar rock came from a small handful of Apollo landing sites, every one of them located on the near side. Chang'e 3 revealed that those samples represented only a fraction of the full picture. Vast stretches of the moon had never been examined directly, and entire regions could still be hiding completely new types of lunar material. But as surprising as that discovery was, it was only a prelude. A few years later, China set out to attempt something no nation had ever managed. In 2019, China launched a mission that many scientists had long considered nearly impossible. Chang'e 4 became the first spacecraft in history to land on the far side of the moon, the hemisphere that permanently faces away from Earth. Because the moon is tidally locked, we only ever see one side of it from our planet. The far side stays perpetually hidden, and that creates a serious technical obstacle. The moment a spacecraft lands there, it loses direct line-of-sight communication with Earth entirely. China's solution was elegant. Before the landing, they positioned a relay satellite called Kuiqiao into an orbit beyond the moon, where it could maintain contact with both the far side and Earth simultaneously. Signals could then bounce between the lander and ground control through this orbiting intermediary. With that communication link established, Chang'e 4 touched down inside the South Pole Aitken Basin, an enormous impact crater stretching more than 2,500 kilometers across, ranking among the largest known impact structures anywhere in the solar system. Scientists believe this basin may have exposed material from deep within the moon's interior, potentially offering a window into what lies beneath the crust. Then came an even more ambitious milestone. China launched Chang'e 6, designed to do something that had never been accomplished: collect and return samples from the far side of the moon. The mission successfully gathered roughly 2 kilograms of lunar soil and rock and brought it back to Earth. Early analysis indicated some of the volcanic rock had formed around 2.8 billion years ago. That finding mattered because it challenged long-held assumptions about when lunar volcanic activity ceased. It suggested the moon may have remained geologically active far longer than scientists previously believed, meaning its history is more complex and more interesting than the textbooks ever recorded. And yet, despite all of these remarkable achievements, the far side is not the ultimate goal of China's lunar program. The real target lies somewhere else entirely. At first glance, the lunar South Pole appears to be one of the most hostile environments imaginable. Towering peaks surround enormous craters that never receive direct sunlight. Because the moon's axis tilts only slightly, some of these craters have remained in permanent shadow for billions of years. Inside them, temperatures can drop below -200 degrees Celsius, colder than almost anywhere else in the solar system. But those brutal conditions may have produced something extraordinarily valuable. Scientists believe these permanently shadowed craters could hold substantial deposits of frozen water ice. And water on the moon is far more significant than it might initially sound. Water can be broken down into its two fundamental components: oxygen, which astronauts can breathe, and hydrogen, which happens to be one of the most powerful rocket fuels ever developed. If those resources exist in meaningful quantities, the moon transforms from a simple destination into something revolutionary, a refueling station in space. Instead of launching every drop of fuel from Earth's surface, future spacecraft could top up on the moon before continuing deeper into the solar system. That capability would dramatically lower the cost of missions to destinations like Mars. This is precisely why China's upcoming lunar missions are concentrated on the South Pole. But before anyone can use those resources, they first have to confirm the resources are actually there. China's next major step in this search is Chang'e 7, currently planned for launch around 2026. Unlike earlier missions focused mainly on broad exploration, Chang'e 7 is purpose-built to investigate the moon's most valuable potential resource, water. To do this, the mission will deploy an entire team of robotic explorers working in coordination. An orbiter will circle the moon from above, mapping the region and relaying communications. A lander will set down near the South Pole. A rover will then traverse the rugged terrain, studying the surface and analyzing the chemical composition of the soil. But Chang'e 7 also carries something never before used in lunar exploration: a small robotic hopping probe. Rather than driving across the surface like a conventional rover, this probe can leap directly into deep craters that are permanently cut off from sunlight, the exact places where standard solar-powered machines simply cannot operate. Inside those shadowed regions, the probe will hunt for water molecules, hydrogen signatures, and frozen deposits embedded in the soil. If it succeeds, Chang'e 7 could deliver the first direct, on-site confirmation of water ice in these ancient craters. That single discovery would fundamentally reshape how humanity thinks about the moon, because finding the resources is only the first half of the challenge. The harder part is learning how to actually use them. Launching construction materials from Earth is extraordinarily expensive. Every kilogram delivered to the moon costs a substantial amount in rocket fuel and engineering. So if humans are ever going to live on the lunar surface for extended periods, they will need to construct habitats from materials that already exist on the moon itself. That is the central purpose of Chang'e 8, planned for around 2028. This mission focuses on a set of technologies known as in situ resource utilization, often abbreviated as ISRU, the practice of using local resources rather than importing everything from home. One experiment will attempt to convert lunar soil into building material. Robotic systems may heat and compress the moon's dusty surface layer, known as regolith, into solid blocks that could be used for roads, landing pads, or protective barriers. Other experiments will explore whether oxygen or water can be extracted directly from lunar minerals. Some proposed designs even involve 3D printing structures from lunar soil, allowing robotic systems to build shelters layer by layer. The vision is that autonomous robots could eventually assemble walls, foundations, and protective domes long before any human crew ever arrives. If these technologies prove themselves in the actual lunar environment, they would demonstrate something genuinely transformative: that humanity does not merely have to visit the moon, but could actually build a lasting presence on it. Once those capabilities are proven, the next phase becomes possible. China's robotic missions are laying the foundation. The phase that follows is human. China is now developing the systems required to send astronauts to the moon, with the stated goal of achieving a crewed lunar landing before the end of the decade. At the heart of this effort is a new launch vehicle called the Long March 10, designed to deliver roughly 27,000 kilograms of payload into lunar orbit, enough to support a crewed landing. The mission architecture is carefully structured and requires two separate launches from Earth. The first rocket carries the crewed spacecraft into lunar orbit. The second launch sends up the lunar lander. Once both vehicles reach the moon, they dock together in orbit. Two astronauts then transfer into the lander and descend to the surface. There, the crew would carry out scientific experiments, collect geological samples, and test new technologies designed for long-term operations. These early missions may last only hours or a few days, similar to the brief surface stays of the Apollo era. But these initial landings are not intended to be the endpoint. China is not setting out to recreate Apollo. It is preparing for something considerably larger. Every piece of this effort, the orbiters, the rovers, the sample returns, the resource experiments, and eventually the astronaut landings, points toward a single ambitious goal: a permanent human presence on the moon. China's long-term project is called the International Lunar Research Station, or ILRS. Formally announced in 2021, it represents one of the most ambitious space infrastructure proposals ever put forward. Its planned location is the lunar South Pole, the same region where scientists believe large frozen water deposits may exist. The station will not materialize all at once. The first phase begins with robotic construction missions. Across the early 2030s, China plans a series of landings designed to gradually assemble the infrastructure needed for a base. Somewhere between roughly 2031 and 2035, multiple missions are expected to deliver the components that will form the station's foundation. These early systems could include communication networks, power generation units, and scientific laboratories. Autonomous robots may handle much of the initial construction, operating on the surface long before any human arrives. Additional systems will focus on resource extraction, experimenting with methods to produce oxygen, water, or fuel from the moon's soil and ice. Initially, the station would function as a robotic research outpost, but over time it is designed to support human crews living and working there for extended stretches. China has also invited international partners to take part, positioning the ILRS as a shared global research platform rather than a purely national venture. If the station becomes operational, it could mark something humanity has never achieved before: a genuine, lasting foothold on another world. This is where the modern era of space exploration enters a new phase. If these plans succeed, the moon could become far more than a target for occasional scientific missions. It could become a foundational piece of a future space economy. The moon offers several advantages that make it uniquely valuable. Its gravity is only about 1/6 that of Earth's, which means spacecraft can launch from its surface using far less fuel. If water ice can be extracted and converted into hydrogen and oxygen, the moon could serve as a refueling depot for deep space missions. Rather than launching enormous, fully fueled rockets directly from Earth, future spacecraft might stop at the moon to refuel before continuing toward Mars or the outer solar system. In effect, the moon could function as a launch platform that dramatically reduces the cost of reaching the rest of the solar system. Beyond transportation, the lunar surface offers something rare for science. Observatories placed on the far side would be shielded from Earth's constant radio noise, creating one of the quietest environments in the solar system for studying the universe. Taken together, these possibilities suggest that whoever establishes the first sustainable infrastructure on the moon may gain a meaningful long-term advantage in space exploration. That helps explain why China is investing so heavily in returning, again and again. When you strip everything down, China's repeated return to the moon comes down to three fundamental motivations. The first is scientific discovery. Even after decades of study, the moon still preserves clues about the earliest history of our solar system. Records that may reveal how planets formed billions of years ago, information largely erased on a geologically active Earth. The second is strategic resources. If water ice exists in large quantities near the lunar poles, it could supply the oxygen and rocket fuel needed to power the next era of space exploration, turning the moon into a stepping stone rather than a final stop. And the third is the largest of all: permanent presence. The moon may become humanity's first long-term settlement beyond Earth, a place where science, industry, and exploration converge on another world. If China succeeds in building that foothold, the next great chapter of human civilization might not begin on Earth at all. It might begin 250,000 miles away, on the surface of the moon.